We are discussing about computation of color constancy, and there the objective is to get color representation which would be invariant to the color of the illuminant. And for that there are two tasks that we have identified. One task is to estimate the color of the illuminant, and the next task is to transform the colors from the source color image to a target color image, where there is a target illumination is desired. I mean, it should be color illuminated by a target illuminator. So, now we will be discussing different approaches of estimating color of the illuminant. So, you consider here that there is one technique which is which assumes that the world is gray, which means that in the red, green, blue, all these components, if I average all the color, then actually your that color of the illuminant would be gray. So, this particular part we can describe in terms of red, green, blue. If I take the average of the red, green, blue components, this one is giving you the color of the illuminant. So, this is that technique is a very simple technique. You have to perform simply averaging of the color vectors, and you get the estimation of the color of the illuminant. The other assumption is called white world assumption. So, in this case the assumption is that the color of the illuminant will be given by the maximum of these components of red, green, blue. The color is almost like white, and you just consider the maximum of their red, green, blue component. And here you need to just compute the maximum of red components of all the pixels, maximum of green components of all the pixels, and maximum of blue components of all the pixels. So, these two are very simple techniques. There are other techniques which require which use more involved computations, and assumptions are a bit different here. Here it is considered that the pixels which are lying on the edges, color of the illuminant, they bear more information of the color of the illuminant. So, the idea is that when colors are reflected by the boundaries of objects, you get kind of a specularity, and as we discussed that specular reflection contains the color of the illuminant. So, from there itself we are trying to estimate the color of the illuminant. So, one of these method that is shown here, it extends pixel based methods to incorporate derivative information. That means, again you are trying to accumulate all such pixels intensity values, and or their derivatives of those intensity values, and then this aggregated form itself will give you the proportional color representations in the 3 vectorial form. So, you just consider these particular computations, and here you can see that we are considering nth order derivative of a intensity value which is represented by the function f x, and c is the channel. I think I have so n is the order of the derivative, then p is a type of norm. As you can see, this is like an LP norm, and this is also called Minkowski's norm in the continuous space, and sigma is the scale. That means, it is smoothed by a Gaussian mask, and then you are performing this derivative, and then you compute this particular computations of LP norm or Minkowski's norm, and for that particular channel C. So, if you are doing it for red component, for example, all the pixels, then you will get a value which is proportional representation of the illuminant for that particular channel, and you carry out these computations for every channel like green and blue. You will get 3 such values, and their proportional values will represent the color of the illuminant, and you can adjust to a particular intensity of that illuminant and transfer the color using the color correction, as I discussed in the previous slides in the previous lecture. The other kind of approach could be that instead of computing the colors or accumulating the responses of the perceived specularities or specularities in pixel reflections, what we can do, we can consider some kind of data driven approach. That means, we have some models of different canonical illuminants in terms of their RGB distribution in a color space. It could be RGB space, it could be XY space, and then given an image, we try to find out what kind of distribution is there in that space. So, the similarity between these two distributions can indicate that whether that corresponding scene has been illuminated by a canonical by that given illuminant whose distribution is known. So, if I have a set of such illuminants, we would try to consider the illumination with the nearest of them, the closest approximation of those distribution, the distribution what we get, we try to attach that illumination with that for that scene. In that way, you can select from a set of canonical illuminants. So, it is observed distribution of points in 2D chromatic space, even you can do it in 3D chromatic space also, that means including intensities. Then you can assign the spectral power density of the nearest illuminant to them. So, there are approaches like gamut mapping approaches. So, as we have discussed that how XY chromaticity chart provides you gives you a gamut, that means the distribution of points in this particular space which should be lying in a triangle, and from there you can compare that distribution with the distribution of the canonical illuminants. So, existence of chromatic points is important. Color by correlation is another approach. So, it depends upon what kind of similarity, how do you compute this similarity. So, it is relative strength over the distribution that is considered. You can use also nearest neighbor approaches, like you can use mean and covariance metrics of those distributions, and some distance functions like Mahalanobis distance function you can use. So, in this way you can select one of these canonical illuminants. Some examples of these techniques, consider this is a target image, and which means this image is illuminated, as you can see there is a reddish hue in the illuminant, and that is why all the points are their color is more tending towards red. But for if I perform color corrections and first you estimate the color of the illuminant using gray world assumption, that means you consider averaging of the red component, green component and blue component, use it as the color of this image. And if I use the target illuminant as simple white light, like with the intensity value say 255, 255, 255, and then perform color correction following diagonal correction rule, then you will get this image. So, this is for gray world method. For max world method, you get this kind of image, and gamut mapping will give you this kind of image. I have not described in details gamut mapping. You can go through some of the papers, and in our course or in this particular respect, we will be considering simple approaches of computing estimating colors using say gray world assumption, max world assumptions, etc. So, let me discuss a problem here, let me solve a problem just to show you that how color corrections could be performed using source illumination and target illumination. So, let us consider this exercise, and then we can understand the computational steps better. So, consider that color of a source illuminant is represented by an RGB vector 200, 240, 180, which means 200 is a red component, 240 is the green component, and 180 is the blue component. Whereas, the target color is given by 240, 240, 240. In my case, as you can see in this example, it is trying to get a white color, white illuminant with this combination, that is a target, and given a color vector 100, 150, 200 in the source image, compute the color corrected vector using diagonal correction rule. So, this is the problem statement. So, let me see how we can perform this computation. It is quite simple and quite direct. If we know these expressions, as I mentioned, we need to first compute the proportional factors of target and source colors of the illuminants for each primary components. Like Kr, Kg, Kb you need to compute, and also you need to compute the corresponding factor for normalizing the colors, so that their some of their intensity values remains still same, some of their or their intensity value remains still the same. So, and then the expressions of modified colors are given in this form. Since they are modified, I am using once again these notations, and if I perform these computations, what is given, you can see Rd, Gd, Bd is given, and the component of source is also given. So, you component these proportional factors by using this information, those values are shown here. Then this color has to be converted into a form as if it is illuminated by the source given by Rd, Gd, Bd, that means 240, 240, 240. So, the computation of f is this is a factor which is computed here, and so color corrected vector as per these expressions are, you can see R becomes 101, it was earlier 100, now after modification it is 101, green becomes 126 and blue becomes 223. So, these are the modified color corrected values. So, you should note that the intensity in this particular computation, if I add R plus G plus B, if I add these values, and that is still coming the same, which is actually with this value is 450. So, if I add 101, 126 and 223, you will still get 450. So, in this correction you are not changing the intensity values of the modified pixels, and but what you are changing? You are changing the relative proportion of 3 primary components, because it is corrected for the target illuminant. So, that is how we perform the color correction. So, this is the final answer of this problem, and as I mentioned, sum of the original vector and the corrected vector remains the same. We will discuss about a more general form of color correction, and that operation is called color transfer. In this operation, what it does, that there is an source image and which has its own color distribution, and there is another image which defines a target color distribution. So, the source image, it would like to borrow the target distribution in its own rendition. So, an example can be cited here to explain this particular operation. Consider this is an image which is that source image, and you can see that source image has an illumination which is a bit reddish illumination, and all the objects inside it, they are affected by that particular illumination. Consider another image which is a completely different image having different types of objects, different scenario, different context, but it defines an illumination or defines a target illumination or target color distribution, which is depicted by this target image. So, it is an image of Alps, a peak of Alps, and so this distribution should be transferred to the content, to the objects of source image, to the display of source image, so that it looks like this. So, your image under this transferred illumination model, or if I say it with the transferred color characteristics, that would look like this. So, here you can see the colors are quite different, and which is quite distribution is quite akin to the target illumination of the as if they are illuminated by the illumination of the target image. So, let us discuss about the processing of this particular operation. So, what we do here, we process all these pixels in a different color space, where we can separate out the chromatic components from luminous components. So, in this particular technique, this is the way this processing has been done. First, the RGB pixels, which are the which are the color, which is RGB is the color space where the color values of the pixels are captured. So, they are converted into another space which is called LMS cone space. So, it is trying to model our retinal sensitivity of different cones. So, it is trying to provide this model trying to provide as if the sensations which will be generated in our cones, and that is what it is trying to capture with this mathematical model. You can see it is a linear transformation, and just to remind you that L stands for long wavelength, M stands for medium wavelength, and S stands for short wavelength, which means they are corresponding to red, green and blue zones of the spectral domain. Now, once you get this LMS value, you further process it, you take it to their log domain, because in some of the perceptual models, it is considered that our perception is more, it follows the logarithmic, it is more proportional to the logarithmic value of the received sensory energy, sensory signals or received energy. So, that kind of heuristics have been used here. We use the logarithmic values and use those logarithmic values to separate out the chroma components from the luminance components. So, you can see once again another transformation, which is also a linear transformations in the logarithmic with the logarithmic values of the cone responses that we have considered in our model. We call it LMS once again, but their font has been shown in a bold font, and you can see the color space which has been given by L, alpha, beta. These are the three components, which is similar to an opponent color space model. You can see particularly in this row. So, this is corresponding to the intensity component, which is the addition of L, M and S, and this one it is L plus M and minus 2S. So, L corresponds to red, M corresponds to green. So, it is like yellow minus blue, that kind of model, opponent color model, and this is L minus M, which is red minus green opponent color model, which we have already discussed earlier. So, it is a variant of this particular operation processing this particular opponent color space. So, we perform this kind of separation. Now, the next what we will be doing, we will be performing certain processings over the chromatic components, so that you can transfer the distribution of colors in the target image to the source image. Let us see how we can do it. So, for modifying the chromatic component and also the luminance component, first what we can do, that we subtract the mean of all those components from the source image. So, you can see here these symbols LS, alpha S, beta S, they denote the corresponding L, alpha, beta components of source image, and then you are taking their mean, which is denoted by this angle bracket operations. I mean, this is a symbol just. So, you are subtracting those means, and then up the subtracted values, they are scaled up so that the standard deviation of the target distribution can be transferred. I mean, your source distribution also should follow the standard, should be similar to the variances or standard deviations of the target distribution. So, you perform a proportional scaling, a scaling in proportion to their ratios of standard deviations that could make these operations. So, you can see here, this is the standard deviation of the luminance component of the target image, and this is the standard deviation of the source component of the luminance component of the source image. So, if I multiply the modified luminance value with this scale, with this ratio, or with these proportional factors, then actually you are making the standard deviation of the modified distribution is the same as the standard deviation of the target distribution. So, that is what you are performing by doing these particular operations, and you are doing it for every component in the same way. So, the corresponding ratios of the standard deviations in those components in both target and source, those are multiplied with the modified values. So, this can transfer the standard deviation operation. So, this is what it just defines the corresponding symbols as I mentioned, that they are the standard deviations of source and target distributions and defining those ratios. So, once you have performed this, then you have to also add the mean of the target distributions components, which means for the luminance components, alpha component and beta component. So, in this way, in the transferred domain, transferred color space or transferred colored values of the source image, in that distribution you are you have transferred the mean. So, that distribution will have the mean which is equal to the mean of the target illumination, target distribution, and also it will have the standard deviation of the target distributions, and that is in the modified L alpha, or that is in the L alpha beta space. And now, the rest of the job should be that you perform the inverse transformation to take all these components into the, take it back to the RGB domain. So, for that what you should do, you should follow the inverse operations. That means, you can see that after modifying the L alpha beta components, again you are taking those values into this space LMS, but this is the logarithmic space of LMS cone space, cone color space. So, this is a logarithmic of LMS cone color values. So, from there again you have to transfer to the original LMS cones color space. So, you perform the exponentiation operations over those logarithmic values and perform once again the inverse operations to transfer from LMS to the RGB value. So, in this way you get the color transferred image from the source image using the characteristics or using the distribution of the target image. So, let me give you the other example of this operation. In this case, we will be considering we will swap the source and target images and we will see its effect, which means your target illumination will be defined by the image which has that reddish illumination in the environment, and your source image will be the image which has been captured in broad daylight in a very sunny day, and it's a once again its content, it has been shown, it's a mountainous peak which is very prominent, and there is a valley, green valley, which has been also displayed. So, under the color transfer operation, let us see how it looks. So, we can see actually the scene is as if it is perceived that it has been captured in some reddish under some reddish illumination, which for natural scene we may consider that it is bit unnatural, in that sense it should not be so much of reddish, but that is what the color transfer operation did. But it would be near, you can say, sunset kind of operations. So, this is just the imaginations through which you can perceive this kind of image. So, next type of processing that we are going to discuss, that is the color demosaicing operation. So, in this problem we use a color filter array. So, first let me explain the principle of the single chip camera, where actually we know that for a camera we require 3 types of filters. For a normal camera, when we have full color reception, which means you have a color signal, suppose there is a color signal, and then you have to receive this signal in the form of a sensor. So, same signal should be received by 3 different sensors. Say there are red, green and blue, and there are different techniques by which the same optical signal is guided to this, or they are divided into 3 different paths, and then they are sensed by 3 different sensors independently, but it has to be the same coherent source, and that coherency has to be maintained to represent the color of a particular object, which should be received by the same signal. Now, this kind of technology is quite complex, and there are different ways people do it, where they have that optical divider and like using prisms, etc. And the manufacturing of this kind of camera requires high technological innovations, and it is quite costly. And since you are using for each pixel 3 different sensors, we call it 3 chip color camera or 3 chip sensors. But there is a cost effective technology for sensing color images, where instead of 3 sensors I will be using only one of them. That means, I can use either red, I will be only sensing red, or I will be sensing sometimes green or sometimes blue. But whenever I am sensing this signal, whenever the camera is sensing any signal of a coming from a particular point, it only captures only one component. But what it does in an interleaved fashion. So, which means that in an image, suppose from the image perspective, if I record the corresponding received energies from different color channels, at this point I will have only red, whereas next point I will have say green, and say this point is blue. So, you can see that I will be losing my spatial resolutions, but if I assume my spectral resolution is much coarse, that means I can associate this blue also to this pixel and this green to this pixel. So, I can consider that all these pixels they have the same RGB values. So, this is a very crude way of estimating the colors. So, that means assigning colors of each pixels, all the full color information, estimating full color informations along these pixels. As you can see, it is a very crude, because I am simply transferring the values of missing components to the neighboring pixels by considering the spatial correlation of the spectral channels. Now, this problem itself, I have just given you one particular solution, but there could be many solutions. It is an interpolation problem, which means I have the missing components and missing components at this point. So, for these pixels, for example, for these pixels, if it is I am recording only red, so my green and blue, they are missing, and but in the neighborhood I have some pixels where those values are there, some are green, some are blue, say some are green, some are blue. So, even I have also other red also. So, considering this neighborhood pattern or this neighborhood information, how best I could estimate these components, missing components. That is the problem of color interpolation. And when we sense the image in this interleaved fashion of one of the spectral components, we call that kind of image as a color filter array. So, let me go back to my slides, so that to summarize this particular computational problem, and this kind of computation is known as color demosaicing or color interpolation. The term demosaicing came as if the pattern, interleaved pattern is called as a mosaic pattern with different color components. So, here you can see that in this problem you are using color filter array of a single chip CCD camera. From there you are generating a dense pixel maps of all the color components. So, they have sparse data as you have only one component at every point, but you would like to get all the color components for every point. And as the motivation, as I mentioned, that technologically it is simple to it is simpler to design and manufacture this kind of cameras, because the coherency of spectral coherency of the reception, to ensuring that coherency is not required here. So, you can use simply the filters in front of the images, in front of your lens, color filters with certain patterns, and for each pixel you will be receiving only energy in that spectral band. So, there are different patterns are proposed by which you can design these filters. That is why the array also is called color filter array, because those are sensed by passing the light, incident light through these filters. So, this example of these patterns are shown here. You can see this pattern, which is called Bayer's pattern, and which is a very popular pattern. In most of the literatures you will find people have worked on this pattern, and you can see that in this pattern what happens, that green red, so they are interleaved in one row. In another row blue green, they are interleaved. So, the fact is that green has been sampled in the color filter array twice the rate than red and blue. So, this is one consideration, is that we are more sensitive to the green channel. So, loss of information of green channel will affect more than the other two components. That is why we have this kind of sampling pattern, but this is not the only pattern. We can have other kind of patterns. For example, there is a pattern adopted by famous Kodak cameras. So, there you have this pattern, like in the same row you have green, blue and reds, on the same row these patterns are interleaved. Whereas, Bayer's pattern we can also identify as if this is the red row, because green is sampled in every row, but in one row when red pixels are sampled, then the next row the blue pixels are sampled. So, rows can be denoted by, for the purpose of describing this pattern or computations, we can say a pixel in the red row or blue row, and whereas columns could be green and non-green. So, either it is red or blue. So, in this way you can identify a location in the Bayer's pattern. You should note also the starting pixel locations and the starting row, starting column and starting rows state. If I can provide you that, and given this particular rule, then I can describe all the patterns. So, in the color demosaicing problem, it is the pattern which remains the fixed. So, you know already that given a color filter array, for each pixel which is the spectral component of that particular image. So, for every pixel I know that which spectral component it is, whether it is green, red and blue, and by following this pattern, if I can tell you one particular pixel, the rest of the pixels spectral components can be determined or described. So, this is the advantage when you use this kind of regular pattern when you describe a color filter array. So, our objective here is to interpolate the pixels, the pixel values in such a way that you get all the full color components, that means all 3 components at every pixel, and that is what is the computation of color demosaicing. So, let me stop here, and we will continue this discussion in the next lecture. We will discuss about different algorithms for performing this color demosaicing. So, let us give a break at this point. Thank you very much for your attention.